Hello, everyone. Welcome to today's session. Add real-time functionality to your .NET applications on AWS with SignalR. My name is Runit Vishisht. I'm a solutions architect in AWS with special focus on helping customers run Microsoft workloads on AWS. I'm today joined with my fellow solutions architect, Matt. Matt, do you want to introduce yourself to the audience?
Sure. Thanks, Runit. My name is Matt Klein. I'm a solutions architect with AWS. I work with digital native customers in the U.S. Northeast region. I've been with AWS for about 3 years, and prior to that, a full stack developer and architect for about 20 years, much of that spent with .NET at a variety of organizations.
Awesome. Thanks, Matt. With that, let's get started. Well, for today's session, we will begin with an overview of ASP.NET Core SignalR architecture and its building blocks. We will talk about things to consider when you're thinking about hosting your ASP.NET Core SignalR application. Then Matt will talk about various options to host and run SignalR applications on AWS, including virtual machines and containers. Matt has a very cool demonstration showcasing the power of SignalR applications in building real-time web apps on AWS. So stay with us till the end. With that, let's get started. So before we go into the details, let's quickly see what is ASP.NET Core SignalR. ASP.NET Core SignalR is an open source library which is used to build near real-time functionality in your applications. Real-time functionality enables server-side code to push content to clients instantly. SignalR is a good candidate to build applications that require high-frequency updates from the server, such as gaming, social networks, interactive maps, dashboards, and monitoring applications. Think of it like this. If you're building an application, maybe a web application, which requires an update to come directly from the backend server without refreshing the browser, SignalR is a good candidate for that kind of application. It supports creating duplex remote procedure calls. These remote procedure calls invoke functions on the client side from the server-side .NET code, and vice versa. SignalR also supports streaming from server to client and from client to server. This is useful for scenarios where fragments of data arrive over time. When streaming, each data fragment is sent to the client or server as soon as it becomes available, rather than waiting for all the data to become available. On the server side, SignalR supports any server platform that ASP.NET Core supports. And on the client side, SignalR supports SDKs for JavaScript, .NET, and Java. But how does SignalR works? Let's look at the building blocks of SignalR. First, to maintain a persistent connection between server and client, SignalR uses one of the 3 transport protocols. First one is WebSockets. It enables two-way persistent communication channel over TCP connections. This is the default and preferred transport protocol for SignalR communication. SignalR provides transport fallback for environments where WebSocket is not available. These fallbacks are server-sent events and long polling. Server-sent events, also known as event source, is used if the browser supports server-sent events, which is almost all the browsers except Internet Explorer. With long polling, the client places the request and the server doesn't reply until it has information to return. Long polling places a smaller number of requests to the server as compared with something like AJAX polling. One of the goals of SignalR is to create an abstraction of this transport protocol so that as a developers, you never have to think about what transport protocol is being used. Essentially, it allows developers to focus on the logic of the application and not thinking about how data is getting transferred. Under the hood, SignalR will choose the appropriate transport depending upon the server and the client capabilities. As a developer, you can focus on your application logic without worrying about the transport protocols. A SignalR server exposes an endpoint which maps to a SignalR hub. Server exposes hub methods which can be called from clients, and the events that clients can subscribe to. These are considered remote procedures. A hub is a high-level pipeline that allows a client and a server to call methods on each other. Think of hub as a proxy between all clients and servers. Hub supports sending messages to all connected clients or to a specific caller or to all the clients in a SignalR user group. Let's see how to add SignalR Hub API in an ASP.NET Core application, which enables connected clients to call methods on the server. First, add SignalR service to the web application builder in program.cs. After that, you will configure SignalR endpoint by calling map hub method and passing the reference of hub class, which is chat hub in this case, and the route pattern, which is /chat in this case. This will allow ASP.NET application to forward any calls made to the chat route get routed to the chat hub class. Now, let's take a look at the chat hub class real quick. You create a hub by creating a class that inherits from hub. Hub class includes a client property that exposes common properties for communication between server and client. For example, all property call in this example will call receive message method on all the connected clients. Similarly, other properties such as caller or group can be used to send messages to the callers or to the group of users at the same time. Now, to communicate with this hub, let's look at the JavaScript client-side code real quick. This reference code creates an instance of SignalR hub connection and invokes server-side send message, passing the calling username and message text. Remember, send message on hub is expected to pass this message to all the connected clients by calling receive message on the connected clients. Here is an example of receive message function, which accepts the username and message from the SignalR server using connection object and updates the HTML with this information. This client-side function can be called from SignalR server. Now, let's look at what are the things you have to keep in mind when you're thinking about hosting an application using SignalR. Let's look at a reference diagram to understand flow of SignalR communication. This is a SignalR social chat application running on server A. 4 clients are connected to the server. Now, client 1 sends a group message for all other clients. SignalR server uses WebSockets to deliver the message to all the clients. Now, let's look at the scaled out implementation of the same application, where there are 2 backend servers hosting SignalR application behind a load balancer. All the clients are connected to the server via the load balancers. This time, when client 1 sends the chat message in the group, the message is received by SignalR server A, but since this server is not aware of client 3 and 4, which are connected to a different server, server B, client 3 and 4 will never receive a message sent by client 1. To support this kind of scaled out deployment of SignalR application, ASP.NET Core SignalR supports shared state management construct called Backplanes. Backplanes uses pub/sub feature to forward messages to other servers. When a client makes a connection, the connection information is passed to the backplane. When a server wants to send the message to all clients, it sends it to the backplane. The backplane knows all connected clients and which server they are on. It sends a message to all the clients via the respective servers. SignalR supports multiple backplane providers. Popular ones include SQL Server and Redis. The Redis backplane is the recommended backplane provider for the scaled out approach. The next architecture recommendation for scaled out SignalR application is to set up sticky session or client affinity on the load balancer to ensure that once a connection to a client is initiated on the server, it has to stay on that server for a longer period of time. At the operating system level, you will be required to enable WebSockets. If your SignalR application runs on Windows, the way you can enable it is by enabling WebSockets feature, either from the server manager or from PowerShell using Enable Windows Operation Feature commandlet. For applications running on something like Nginx, you can enable SignalR applications by ensuring that you have configuration set up for WebSockets, server-sent events, and long polling on Nginx config. Here is a sample or a reference config which enables all of these settings. Now that we have talked about how SignalR works and what are the architecture considerations to keep in mind for SignalR, I'm going to hand it over to my friend Matt to talk more about a sample application and show you SignalR in action. Over to you, Matt.
Thanks, Ronit. So I know the canonical SignalR demo is a chat application, but we're going to do something a little bit different today. The demo we have here is for a delivery company that's operating in Pittsburgh. They have a fleet of trucks making deliveries all over the city. And we have a web app here for our dispatchers to use, our dispatcher dashboard. This will help dispatchers monitor the locations of every truck in the fleet. Now, each of these trucks has an app running in it that's connected to our SignalR hub. And so every so often, the app is going to get the truck's position via GPS and send it to the SignalR hub. And we want to update these positions on the map for dispatchers in real time. By the way, we're using Amazon Location Service to provide the map, as well as store the truck locations in a secure way. This is a trucking-specific map. You can actually see that some roads have weight or height limits, and others prohibit trucks entirely. I'm going to go ahead and open up the browser console here so that you can see the messages that come in, and you can see our existing messages. We've already made a connection here to our SignalR hub. So I have a command line app that's going to simulate a fleet of trucks. Each of those trucks has its own SignalR connection and sends randomly generated location data to the hub. Now, the simulator is operating at 10x speed, so you'll see trucks moving at unsafe velocities. So please don't drive this way at home. Let's go ahead and start our simulation. And let's use 6 trucks. Whoops. Here we go. So our trucks are connecting, and you can see in the console, they're starting to send data to our SignalR hub, and now we're seeing the trucks show up on the dashboard, and their positions are updated in near real time. Again, as these trucks are careening around the city at unsafe speeds, they're sending their positions to the SignalR hub. The hub is notifying all of the connected dispatcher dashboard clients of the new position for that truck. Then the dashboard app, which is running the SignalR JavaScript client, is getting an updated truck position from the hub, and so it'll update the position of the corresponding marker on the map. So as this runs through, the trucks will complete their deliveries and then come back to headquarters where they'll stop being tracked. So let's take a look at the AWS services that make all of this work. So the Dispatcher Dashboard web app is running in a container using Amazon Elastic Container Service, or ECS. ECS is a container orchestrator developed by AWS. And so the ECS service here is maintaining 3 tasks or 3 containers for the Dispatcher Dashboard web application. Each of those tasks, again, is one container that's running the ASP.NET Core website for the Dispatcher Dashboard app. Now, ECS makes it really easy to integrate load balancing. It'll automatically add and remove containers from the load balancer as they start and stop. This integration happens through a target group, which is a group of instances or IP addresses that the load balancer uses to distribute traffic. So you can see under this service, we've got a target group here. And if we go over to that target group, we have 3 registered targets, 1 for each container. And the IP addresses that are registered in the target group actually match the IP addresses of our containers. So we can go ahead and here into our task. Let's click on one of our tasks, and we can scroll down here and see the private IP. So this one is 169.84. And if we go back over to our target group, you can see here we've got 169.84 in the list of targets. That integration happens automatically with ECS. When a new container starts up, ECS automatically adds its IP address to the load balancer, and when the container shuts down, ECS automatically removes it from the load balancer. Now, our SignalR hub is running in much the same way. It's in an ECS service. The only difference is that this service is only running one task. It's running a single container. It is integrated with its own load balancer, but again, we're only using one task here. So if we go over to the corresponding target group, and we'll refresh the list here, you can see that we've only got one target in our load balancer target group to match the one task that's running in ECS. Now, that's a limitation of this architecture. We're only running a single container for the hub. Now, this is an important dashboard for us, so we'd like to have some redundancy here. We've already scaled up our web app, so it's running on 3 containers spread across multiple availability zones. So let's do the same thing for the hubs. So I'm going to use the AWS CLI to update our hub service here and add 2 more running tasks. Now I'm going to do that through the AWS CLI with this command. You could also do this through PowerShell or the console or the CDK or Terraform or even a raw API call if that's what floats your boat. So we've gotten back a JSON response here that indicates success. So let's go back to our service and see what's happening. So I'm going to hit refresh here, and you can see we've got 2 more tasks that are starting to come up. And if we go back to our target group, as those tasks are registered, they're going to show up here in the target group. The load balancer is going to do some initial health checks to make sure that those containers are healthy. And once they are, it'll add them to the load balancer as it just did. Okay, so now our containers are running, they're registered with the load balancer, they're good to go. Let's go ahead and run our simulation again and see what happens. Okay, so we can see our trucks are connecting and they're sending position updates, but we're not seeing the entire fleet on the map. So the reason why that's happening is that each of these trucks is making its own connection. Those connections are getting routed by the load balancer to one of our hub containers. And our dashboard here is also connecting to one of those hub containers, but the hub containers aren't communicating with each other. And so the web app is only getting updates from the trucks that are actually connected to the same hub that it is. So to fix this, we'll need to set up a Redis backplane. Now, I've actually already set up another ECS service to show this. So this ECS service is exactly the same as the current hub service, except the container is running with an environment variable that contains a connection string to a Redis server. Now, the Redis server in this case is an Elasticache for Redis instance. And so when I've set up this Elasticache for Redis node, I'm going to get the primary endpoint here, and that'll serve as my Redis connection string. So if I go over to ECS, take a look at the tasks. So I've got 3 tasks running here. Let's go into one of these tasks and expand the containers. And I can see we've got an environment variable in here, AWS SignalR Redis connection string. And that value here matches the primary endpoint of our Elasticache for Redis instance. So the code in the hub is going to look for this configuration setting, and if it finds it, it's going to use that as its Redis backplane. Now, since these 3 tasks are already running, I can actually go in to our hub load balancer And I'm going to change the listener here to send the traffic to the Redis backplane target group instead of the standard hub with no backplane target group. Go here to the listener and select edit. And I'm going to forward it to the hub Redis target group. And save changes. Okay. So now I can see that our load balancer for the Redis, for the hub service is actually going to be sending traffic to the containers that are running with a Redis backplane. You can see here we've got our Redis target group. So let's go back and rerun the simulation and see what happens. I'm going to reload the web browser. It was showing an error there because it got disconnected from its hub because we switched the load balancer. So we'll reconnect here. Okay, SignalR connected, so we're good to go. So let's go ahead and run our simulation again and see what happens. And there's our full fleet of 6 trucks. So that Redis backplane, hosted in a fully managed Amazon Elasticache instance, is coordinating among the hub containers. Now, when a hub sends a message to all dispatcher dashboard applications, that message goes across to every client connected to every hub. So our dashboard sees the full view of the fleet. So that's our demo. Let's unpack the AWS resources that are used in the demo and show you a little bit more about how they work. So here's the architecture of the first demo. We have our web application that's running an Elastic Container Service with several containers deployed behind a load balancer. Our users are connected to the website through the load balancer and load the dashboard web app. Now, those same users also make an ongoing connection with the SignalR hub, which is also running an ECS behind its own load balancer. So, when one of the trucks in the fleet connects to the SignalR hub and sends its position, then the SignalR hub is going to send a message to all of the connected clients, and they'll show the truck's position on the map. Now, when we first tried scaling up the SignalR hub without a backplane, well, that caused some problems. So our truck is going to send its position to the hub container that it made a connection to through the load balancer, and then that hub container is going to send the same message to the users that it was connected to, but that means that users that were connected to a different hub container through the load balancer didn't get the message. To fix this, we added a Redis backplane. Now, when a truck sends its position to one of our hub containers, the container is then going to propagate that message through the backplane to all of the other containers. And then each container will send the message to the clients that are connected to it, which means that no one is left out. Every client receives every update. So that's how the demo worked. But the demo showed just one possible configuration of a SignalR application on AWS. Let's talk about some of the options you have to host your SignalR application and all of its components on AWS. Now, to host a web application, there are a variety of options on AWS. You can use a virtual machine with EC2. You can run a container on ECS like we saw in the demo. Or you can use our managed Kubernetes service to run containers. You can run an ASP.NET Core web application in a Lambda serverless function. And if your website is purely static, say if it's written in Angular, React, Vue, or another sort of client-side framework that has no server-side component, you can even host that application in S3 for huge scalability. Now, most applications have a web API that's separate from their SignalR hubs. On AWS, you can host this in a virtual machine on EC2, or in a container with ECS or EKS, or you can run your API in a serverless Lambda function. Now, for your SignalR hubs, Microsoft recommends hosting them separately from other application components so they don't compete for resources such as TCP/IP connections. So to host a SignalR hub, you can do that in EC2, in a container in ECS, as we saw in the demo, or with EKS if you want to run Kubernetes. Now, as we saw in the demo, AWS's elastic load balancing works with SignalR. Application load balancers support HTTP and HTTPS traffic. ALB also supports SignalR's WebSockets transport mode. They can load balance based on round robin or a least traffic algorithm, but when you're setting up a target group for SignalR, be sure to enable sticky sessions on that target group to make sure that connections stay persistent so that one client is connecting to the same server for the lifespan of its session. Finally, for a SignalR backplane, you can run your own Redis server on EC2 or in a container if you want to, but AWS has two fully managed Redis services that will work as a SignalR backplane. They are Elasticache for Redis and MemoryDB for Redis. Both of these are Redis-compatible data stores that are fully managed by AWS. So how are they different? Well, Elasticache is designed to accelerate another persistent data store, and MemoryDB is designed to be a primary data store. So Elasticache is typically more economical to run, and MemoryDB has high durability. In general, I recommend using Elasticache for a SignalR backplane. It's fully managed, so it minimizes the maintenance that you need to do. And most SignalR traffic doesn't need to be highly durable, so the advantages of MemoryDB don't really come into play in this use case. Oh, and whatever you use, I highly recommend you run Redis on a Graviton instance. Graviton is AWS's custom-designed ARM CPU. For fully managed services like Elasticache and MemoryDB, Graviton is an easy choice because there's no extra effort on your part. And for .NET workloads, whenever you can run them on Graviton, you should. They'll be both faster and cheaper. You can actually use Graviton on all of the compute options we've mentioned here, EC2, containers, and Lambda. So let's sum up. Yes, you can indeed run SignalR on AWS. You have a variety of options to host SignalR hubs, including EC2 virtual machines or containers with Elastic Container Service or Elastic Kubernetes Service. Application Load Balancer works great to distribute traffic among your SignalR hubs. Just make sure you have sticky sessions enabled, and if you have multiple hub instances or containers, make sure you have a Redis backplane set up so that those hubs can coordinate with each other. And to do that, you can use Elasticache for Redis or MemoryDB for Redis as a fully managed backplane, so you don't have to do any of the setup or maintenance on that Redis server. Thank you so much for your time today. We really appreciate it. Thanks for Renit for kicking us off, and enjoy running your SignalR hubs on AWS.
Thanks, everyone. Thanks, Matt.